Hello, future engineers. Welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends, to your younger brothers and sisters who would want to take up engineering in the future, and to your relatives. That's one way you can keep me going, inspired, and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. Hello, future engineers, subscribers, viewers, and students. There is another video in calculus on limits and continuity. I hope that this video will help you grow and improve, especially your thinking skills needed in calculus and also in higher subjects for you to analyze and easily understand the concepts of other higher engineering subjects in your field. If you want to anticipate the solution to these exercises, you can by pausing the video and answer them. So here are the problems. Problem 1, let alpha in degrees denote the measure in degrees of an angle whose radian measure is alpha. Use the fact that sine of alpha in degrees is equal to sine of alpha and that alpha in degrees is equal to 180 degrees over pi times alpha, because alpha in radians should be, if we convert alpha in degrees to radians, we have to multiply alpha degrees by pi over 180 degrees. Therefore, alpha in degrees is 180 degrees over pi times alpha. So together with the appropriate theorem to show that limit of sine alpha in degrees over alpha in degrees as alpha in degrees approaches 0 is equal to pi over 180 degrees. So as a proof, let's have this solution presented here. So limit as alpha degrees approaches 0 is sine of alpha degrees over, we replace alpha degrees here by 180 degrees over pi times alpha, which is now in radians. Now, take note that sine of alpha in degrees is also sine of alpha in radians. So I replace this with alpha in radians. So equals limit as alpha in degrees approaches 0 of sine of alpha over 180 degrees over pi times alpha. Then we simplify this and write this into pi over 180 degrees. Then limit as alpha degrees approaches 0 of sine alpha over alpha. And the limit of sine of alpha over alpha as alpha in degrees approaches 0, because as alpha in degrees approaches 0, alpha also approaches 0, just like here. And we note that limits of sine alpha over alpha as alpha approaches 0, alpha in radians now, because when alpha in degrees approaches 0, it is also the same as alpha in radians approaches 0. So this is equal to 1, and this is the constant, therefore the limit is pi over 180 degrees, which is that. So it is equal to pi over 180 degrees. Problem 2, show that if the polynomial in x, p of x is a polynomial in x, limit of p of x as x approaches a is equal to p sub a, the function value of the polynomial when x is a. So take note that the polynomial curves are continuous. There's no gap, there's no break, and the limit as of the polynomial in x as x approaches a always exists left and right. So that's why it, it exists, and the function value also exists. And because the condition for functions to be continuous is that the limit of the function as x approaches a must be equal to the function value when x is a. So limit of p of x as x approaches a exists. The function value when x is a also exists, and the condition for continuous function is that the limit as x approaches a is equal to the function value of the polynomial when x is a. So I put here the necessary conditions for continuous functions. So this is a necessary condition or requirement for a continuous function or continuous functions. Problem 3 showed that if polynomial in x, p1 of x and p2 of x are polynomials, limit as x approaches a of p1x over p sub 2x equals p1a over p sub 2 of a, where p sub 2 of a is not equal to 0 or not an indeterminate case. So by the preceding problem, the polynomials are continuous, so that the limit of p1 of x as x approaches a exists, and it is equal to p sub 1 of a from the condition here. Limit of p sub 2 of x as x approaches a is equal to p sub 2 of a, which is also the same situation in problem 2. So therefore, the limit of p1 of x over p sub 2 of x as x approaches a is p1 of a over p sub 2 of a. And that's it. That's the showing of the fact that it is equal to that. Problem 4. Under what circumstances may the limit in problem 3 exist? When the function value of 2 as when x is a is 0, give examples. Even if the denominator approaches 0, the limit still exists as long as the factor that will make the denominator 0 can be cancelled, or there is also a common factor similar to that in the denominator, and there is also a common factor in the numerator that can be cancelled so that it will not approach 0. So when limit of f p1 of x as x approaches a is equal to p of a and it is 0, this is the explanation. It is also the polynomial in x in the numerator also approaches 0, and the common factor is x minus a, which is also the factor in the denominator. That's why p of a is approaching 0, or p sub 2 of a is 0. And these are the examples. So example 1, p1 of x is equal to x squared plus x minus 2. And when x approaches negative 2, this is negative 2 squares of 4 plus negative 2 minus 2 is approaching 0. So p of 2 of x is x squared plus, this is the second polynomial, x squared plus 5x plus 6. And limit as x approaches negative 2 of x squared plus x minus 2 is the function value when x is negative 2, and that is 0. So negative 2 squared plus negative 2 minus 2 is also the function value when x is negative 2. It is 0. It is approaching 0. In fact, it is exactly 0 when x is negative 2. But for this limit here, it only approaches 0. For limit of the second, x squared plus 5x plus 6, as x approaches negative 2, it's also approaching 0 because we have negative 2 squared plus 5 times negative 2 plus 6. So 4 minus 10 is negative 6 plus 6 is 0, almost 0. So p sub 2 of negative 2 is 0. So that still the limit exists, and let's factor the numerator as well as the denominator. And we have limit as x approaches a of p1 of x over p sub 2 of x, where p sub 2 of x is 0, and limit of p1 of x over p sub 2 of x as x approaches negative 2 So we have p1 of x, p sub 2 of x. Let's write them in factored form. So limit as x approaches negative 2 of x plus 2 quantity x minus 1 over x plus 2 quantity x plus 3. So we can cancel x plus 2 because x approaches negative 2 and not equal to negative 2. So it reduces to limit of quantity x minus 1 over x plus 3 as x approaches negative 2. And this is negative 2 minus 1, negative 3 over negative 2 plus 3, 1. So it is negative 3. So the limit exists and it is negative 3. So even if the function value of the denominator is 0, the limit still exists. Another example is these polynomials p1 of x is equal to x cubed minus x squared plus x minus 1, and p sub 2 of x is x squared plus 3x minus 4. So in this case, as x approaches 1, these polynomials approach 0. So p1 of 1 is equal to p2 of 1 equals 0. We just evaluate these polynomials. 1 cubed minus 1 square is 0, plus 1 minus 1 approaching 0. Same is true here, 1 square plus 3 times 1, 4 minus 4 approaching 0. So writing in factored form, limit of x cubed minus x squared plus x minus 1 over x squared plus 3x minus 4 is limit of quantity. So you have to factor this by synthetic division. It's up to you. The denominator, we can factor that easily, x minus 1, x plus 4. So we can cancel x minus 1, and the limit is 1 square plus 1, 2 over 1 plus 4, 5. So 2/5. So limit of as x approaches 1 of p1 of x over p sub 2 of x. Even if the function value of the denominator approaches 0, the limit still exists. And in this example here, it is equal to 2/5. So these are the just two examples. We can have more, but I think these two examples are enough for this problem. And problem 5, show by means of an example that the limit in problem 3 does not always exist when p sub 1 of a equals p sub 2 of a equals 0. So this time, I will show that the limit will not always exist. In the preceding problem, we showed by means of examples that the limit can still exist. But this time, I'll give you one example where the limit does not exist when the function values of both the numerator and denominator approach 0 or equals 0. So p1 of x, this is the example, x squared plus x minus 6. And p sub 2 of x is x cubed minus 3x squared plus 4. And as x approaches 2, these functions approach 0. So p1 of 2 is 2 squared plus 2 minus 6, so that's 0 exactly. P sub 1 of function value when x is 2 for polynomial 1 is 0. P sub 2 of 2 for polynomial 2 is 2 cubed minus 3 times 2 squared plus 4. So 8 minus 12, negative 4 plus 4 is 0. So P sub 2 of 2 is 0. So the limit, and we write them in factored form of p1 of x over p sub 2 of x as x approaches a, is limit as x approaches 2 of the factored form of the first polynomial. We write it first, x squared plus x minus 6 over x cubed minus 3x squared plus 4. Because both approach 0, there is x minus 2 as a common factor. So this is x minus 2 times x plus 3 in the numerator. X minus 2 times x plus 3 in the denominator, x minus 2 square times x plus 1. So take note that we can only cancel x minus 2, and we simplify this into limit as x approaches a of p1 of x over p sub 2 of x is limit as x approaches 2 of x plus 3 over quantity x minus 2 times x plus 1. Since as x approaches to this x minus 2 approaches 0, and we cannot eliminate this anymore or cancel this anymore. Therefore, that's the case. This is the case where the limit when the function value of the denominator when x is equal to a approaches 0 or equal to 0 does not exist. So this is just one example where the limit does not exist. So that's why when p1 of a equals p sub 2 of a equals 0, the limit of the ratio will does not always exist. And this is just one example. We can have many more, but I think this is enough. So that's it for this video. I hope that you enjoyed watching and you learned something from here, which is necessary for your future or higher engineering subjects.